Welcome everyone. In this video we are getting into the basics of circular motion, things moving in, well, circular paths. So we're really going to start by looking at the basics of motion, and that includes speed and acceleration. And we of course have learned those terms previously. We're going to start applying them to this circular motion. So to begin, a common term or a common phrase that's describing this topic we're in, and that's uniform circular motion. And it is defined just how it sounds. It's the motion of an object that's traveling at some constant, some uniform speed in a circular path. Now, to be honest, a little bit later we'll look at some examples of when things aren't moving in a constant speed, but we'll apply this scenario to most of our examples. So things moving in circles and things moving with a constant speed. And here's a very classic example that I'll be using throughout this video. Here we have a person and they have like a toy airplane and it's attached to a string. And they're spinning that toy around and around and around. We'll assume it's like a horizontal circle. And they're spinning it with the same speed. So if you look at all these V's, these little velocities, assume this plane is moving in a constant speed as it's going around in a circle. Okay? So the first part of our notes, part A, average speed. Again, we'll apply it to this same example here, just so we have a nice visual. We already know what average speed is, the basics. It should be the distance an object travels divided by the time it takes for it to travel that distance. Okay, now before we would do like x over t or d over t, distance over time. But now we know very specifically that this object is moving in a circle, so the distance, every time it makes one revolution, it travels the circumference of a circle. I'm really hoping I'm not going to spell circumference wrong. And the time would be the time to travel that circumference. Okay, the time to travel. Well, I know the equation, or hopefully we know the equation for the circumference of a circle. It's 2 times pi times the radius, where the radius is this right here. Can't draw a straight line, but right here, this is r, the radius of that circle. So it's traveling all the way around there. It's traveled 2 pi r divided by t. So that's average speed. This t is often rewritten, though, not just as our kind of regular lowercase t, but it's a very specific t. It's the time for one revolution. So often we'll see this equation, 2 pi r over uppercase T. That's actually the same symbol we use for period, like the period of a pendulum. Remember that period was the time for one complete motion, and that's actually kind of applicable here. We have the time for one complete motion, and then it starts over again. Okay, but this is just the time it takes to go in that circle. Okay, I know I have V here. We're really talking about speed. It doesn't really make a whole lot of sense to talk about our classic average velocity because, of course, when the plane gets all the way back, its displacement would be 0. So I know there's a V here, but when we're using this equation, when we're talking about the average rate something's moving in a circle, we're technically talking about speed. Now, tangential velocity does come in handy, but this is different. I'm not saying the average rate that plane is moving in a circle. I'm saying essentially at one instance, at one moment in this path, how is the object moving? And that's what this is showing. This is representing a tangential velocity. Okay? Because if we freeze frame this motion right here, the plane is right here. Of course, the string is connected. Okay? The plane, if we zoomed in and if we had this on a slow-mo camera, it's right here to start. And one moment later, if we move the image ahead one frame, the plane would be here, right? It's going from this location to this location. It's essentially moving like this. Same thing, when the plane is here, at one moment it's right here. The very next instant, if you imagine a nanosecond, the plane would be right here. So if we're really limiting our time, I'm not talking about the average, but in an instant, or essentially an instant, the plane is always moving. It has a displacement and it has a velocity tangent to that circle. All right, so this is that momentary velocity, and it's always just tangent to that circular path it's traveling in. We're not really going to worry about an equation right here. Sometimes you might see this represented as VT, the tangential velocity. Just note these two things are different. This is the average speed that the thing has as it's going around. And this is, of course, the velocity it has at one moment, where it has an approximate distance over time, you know, a nanometer over a fraction of a second, and some direction. All right? Well, if that's the case, if this plane does in fact have these tangential velocities, Well, let's think. That tangential velocity, while we zoomed in, notice it's changing. Of course, the plane is moving around and around in this circle. The tangential velocity's direction is changing. Well, velocity is a direction. That means tangential velocity is changing, and it's constantly changing, right? You're going around and around the circle. What's it called when you have a changing velocity? You must have an acceleration. Because remember, acceleration by definition, it's defined as delta v. And v is based on direction. So even if the speed of the airplane is staying constant, this tangential velocity, its direction is always changing. Therefore, it does in fact have a change in velocity. Therefore, it must have some acceleration. That's why I have this term here. You might have thought, well, wait a minute, if it's moving at a constant speed, why are you talking about acceleration? Well, the velocity, these tangential velocities are changing. So you must have an acceleration. That's really the only other thing we're going to look at in this video. Okay, what exactly is this acceleration? We'll see in an equation. And where does this centripetal come from? All right, that's what we're going to focus on right now. If I was looking at these two locations, I see the velocity here and I see the velocity here. I can look at the change in velocity. Remember, that's the subtraction of the two, v minus v naught. Okay, now these are vectors right here. And I'm just going to do a little vector stuff. Normally when we have vectors, when we add them, we use the process called like heads to tails. So I would take this vector right here. So take like this one, and then I would add head to tails this one, just like this. Oops, excuse me, just like this. And then that result, that would be our resultant direction. But I'm not adding vectors here. I'm trying to subtract vectors. So I shouldn't really be doing this combined with this. When you subtract vectors, you're adding the opposite. So instead what I should be doing is, I'm going to draw this one like before. That's this thing right here. But instead of drawing this one like I had drawn right here, I need to draw the opposite. And that opposite would be like this. So if I call this A and B, this is my vector A. This is my opposite vector B, because I have to subtract it. And my result looks like this. I then connect. The word centripetal, it means center seeking. And this is why it's called centripetal acceleration. What direction is that change in velocity? It's towards the center of my circle. The objects are accelerating, and it's a little weird. The accelerations are always towards the center of the circle. Here's another diagram if this is a little easier for you to copy down. Key idea, the acceleration of objects moving in a circle. Acceleration of objects, I'm going to write down in uniform circular motion, is always toward the center. Hence the word centripetal, toward the center. Oh God, thrasher. Center, just like that. All right, so that's a key idea. Here's an example right here. If we have an object that's now spinning this way, it has right here a tangential velocity like this. Here it has a tangential velocity. When you subtract them, because remember, we're subtracting. It's a change in velocity. Here's v. Here's you adding the opposite. Okay, oh, they actually did it a little different way. If I did it my way, I'd be doing this combined with not this, but this. That's the opposite of this thing right here. So you're left with right here. Okay, but that acceleration, that change in velocity is always toward the center. Okay, now there is an equation for the acceleration of an object moving in a circle, this centripetal acceleration, and here's the equation. We're not going to derive it. It requires a little bit of geometry that we don't need to get into. You could Google centripetal acceleration if you wanted to see the derivation. It's just a little bit beyond the scope of this course. But the centripetal acceleration, so A with a little c, that's what this is referring to, it's equal to v squared divided by r. Where v is this speed, we're just worrying about the speed. So you could either have used like this value right here, or if they told you the tangential velocity, that would actually be the same, right? We're assuming this speed is constant. So you plug in just the speed of the object squared divided by r, again, r being the radius. So there's two things you should hopefully take away from this video. One, we have an equation for circular speed and centripetal acceleration, and that acceleration is always, 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 always toward the center of my circle. All right, thanks for watching.